So, we will come back to this thing, right. Therefore, you will this thing just hold on. So, this is that expression for receiving end 3 phase power, right. This is equation 79, right. Next, what you do, this one, this angle delta b minus delta s. So, you can write this term cosine delta b minus delta s plus j sin delta b minus delta s. Here also this one cosine delta b minus delta a plus j sin delta b minus delta a. So, multiply and then you separate real and imaginary part, right. So, if you do so, then it will be receiving end 3 phase power, it will be mod V s L L into V r L L, that is line to line voltage by mod B magnitude cosine delta b minus delta s minus a mod a V r line to line square by mod b cos delta b minus delta a. This is equation 80, right. And similarly, this one your reactive one V s L L V r L L upon b sin delta b minus delta s minus mod a V r L L magnitude square upon b sin delta b minus delta a. This is equation 81, right. This is receiving end. So, this is an exercise for you, you find out for the sending end side, but I am giving you the final expression. Similarly, we can obtain sending end one, right. So, it is P s your sending end 3 phase power, it is a V s L L square upon mod b cosine delta b minus delta a, right, and this is V s L L V r minus V s L L V r L L upon mod b cos delta b plus delta s. This is equation 82. And similarly, Q s is equal to that is the 3 phase a V s L L square upon mod b sin delta b minus delta a minus V s line to line V r your line to line all magnitude by b magnitude sin delta b plus delta s. This is equation 83. So, real and reactive power loss easily you can find sending end real power minus receiving end real power, that will give you 3 phase real power loss. So, P loss 3 phase P s 3 phase minus P r 3 phase and Q loss 3 phase will be Q s 3 phase minus Q r 3 phase, right. This way you can calculate the loss. This is another way of calculating, there are many ways. So, this is another way of calculating. So, this performance and characteristic of transmission line, this particular topic will be I think here we will stop, right. And as far as possible we have tried to understand the things of characteristic of transmission line, right, and whatever possible things are available, this thing are I mean important, we have tried to discuss, right. So, this characteristic of transmission line, this thing is over. Next one is that most important one is that your power flow or load flow studies, right. So, in this case for next one 1.5 hour or so or about that, what we will do, I have written your rather horizontal, written it vertically, right. So, load flow this thing you have to you have to try to understand little bit, right, and that particularly this topic actually involves as you know that involves huge mathematics, and when this transmission line load flow will be your load flow or power flow analysis will be covered at the end. I will give you one latest thing, that is that P bus and P Q V bus, that is at the end how to form the Jacobian matrix, but here in the classroom teaching also we can take we cannot show, we can take a small example, because this is a topic where you need computer and you have to write code. Although nowadays so many your what you call your packages or codes are available, but in that case what is happening that in that code you are giving input and getting the final result, that is fine, right. But my question is that if you try to write code of your own, then definitely you will learn many things, right. So, this load flow analysis will will go step by step, and what we will do that every step or every line please try to understand for this load flow studies as much as possible. From my side I will try. So, load flow analysis or power flow studies commonly referred to as the load flow, right, essential for power system analysis and design both, right. So, basically load flow studies are necessary, that planning, economic operation, scheduling and exchange of power between utilities. You need that load flow thing, right. Apart from this load flow or power flow is also required for transient stability, that small signal stability, sometimes we call dynamic stability, contingency and state estimation, right. So, everywhere that load flow is required, right, and node voltage method is commonly used for power system analysis, right. Therefore, this load flow results give the what it will give? It will give you the bus voltage magnitude, right. Then it will give the your voltage phase angle, that is the voltage angle, right, and then power flow it will give through the transmission line losses you can compute, right, and the power injection at every bus bar, right, that also you can compute. So, and whenever we do so, we have to see that how we can make it, right. So, basically in load flow, that you have to first classify the bus bars, the bus bar classification, right. So, basically 4 quantities are associated with each bus, right. So, these are actually voltage magnitude, this is voltage magnitude that V, then phase angle your delta, and real power is equal to P and reactive power is Q, right. Therefore, in load flow studies at least 2 out of 4 quantities are specified, right, at least 2 you have to specify, and the remaining 2 quantities are to be obtained through the solution of equations, right. But let me tell you these are the common thing, but we have a slack bus, we will come to that, you have a your what you call PQ bus, you have PV bus, right. Apart from that, nowadays as electrical engineering is changing, right, because of that your smart grid, microgrid and renewable energy sources, particularly solar and wind or other types of sources, right, that dispatchable DGs and non-dispatchable DGs all are coming and in your heavy power injection into the power network. So, that is why many cases that apart from this many other type of buses are being introduced, right. P and PQ bus is one thing, and some other thing also you can make it, right, as per your requirement. So, for example, if you make suppose for although at a third year level or even at PG level also, this is not this may not be very familiar with you, for say when a distribution network actually working your under islanded mode, that is it is not connected to the grid, right. So, at that time you will find load flow is different, right, a load flow is completely different, and at that time that particularly that dispatchable DGs like your say biomass DG or diesel generator, one has to consider the droop characteristics, right. So, in that case that Jacobian matrix whatever we will see in the load flow studies, it will become that function of your what you call that frequency also, right, the Jacobian matrix, and in that case of course, you can follow the same Newton-Raphson method, but with lot of modifications, right. So, things are changing and electrical engineering also changing, particularly the power system engineering is changing like anything, right, because of the smart grid and microgrid, although those things are beyond the scope of this course, but I am giving you some hint of this one. And for distribution power flow, although Newton-Raphson method works well, couple of your couple Newton-Raphson method it works very well, but at the same time some other types of load flow techniques also available for distribution network, because distribution networks actually mostly it operates your radially, right. I mean and your what you call transmission based network, more it is actually meshed network, right. So, 4 quantities for load flow studies we will basically handle. The system buses as classified, one is first one is that slack bus. This is sometimes also called the swing bus and taken reference when the in this bus actually voltage magnitude and phase angles, these two are specified, right. And I told you that your what you call that here you are taking slack bus, but when you are coming to your what you call that sometimes for microgrid, DC microgrid, there we can also see that your slack bus free actually, right. Anyway, those are beyond the scope. So, this bus provides the additional real and reactive power to supply the transmission losses, that is the slack bus. We have to choose one reference bus and result will come around that your what we call that slack bus, right. Since these are unknown until the final solution is obtained, because this slack bus actually provides the additional real and reactive power to supply the transmission losses, and these are known until the final solution is obtained, because unless and until your load flow solution has converged, you cannot do anything, right. You cannot compute the loss also. Now, another thing is load bus. Sometimes we call this one as a PQ bus. That means, load bus PQ bus means that at that load that P and Q both are specified, right. That means, in that bus you will find that power injection P and Q both are known, right. That and magnitude of the voltage of this bus and its phase angle, these two are unknown quantity, and you will be knowing only when you will solve this load flow this thing in iterative way, right. So, unless and until you final solution is not obtained, you will never be knowing the magnitude and voltage angle, but P and Q both will be your what you call this thing are this thing specified at the load bus, right. Then another bus is called voltage control buses or PV bus, right. Here that real power is known, P is known, and voltage magnitude is known. That is why we are this is called sometimes this is called generator buses or regulator buses or simply PV buses. P I put magnitude V buses, because P is known and voltage magnitude is also known for this bus. Then what is unknown? Q is unknown, and your what you call that voltage angle, it is unknown, right. These two are unknown. That means, that PV buses, right, that your what you call that voltage magnitude of that bus you want to maintain, right. As P is known, voltage angle is not known, but Q is unknown, right. That means, at that bus you have to inject that reactive power such that you can maintain this voltage magnitude V for that bus. So, this is called sometimes we call PV bus, right, or generator buses or regulator buses, right. So, and in that case that as Q PV buses Q is unknown. So, you have to also set the limit on the Q injection, that is some minimum value to maximum value. But let me tell you one thing, as it is a classroom exercise. So, taking Q mean, Q max, all sort of things, it is difficult to put in the classroom. One need code, computer code one has to write, and one should observe what is happening. But in this case, in this thing, it will take I think few hours to explain all sort of things, but I will take throughout this load flow studies, I will take only one example and give all sort of your what you call this thing methodology, right. So, Q limit also you have to consider, and it has to be specified for PV buses, right. Therefore, the following table summarizes the above discussion, right. So, bus type, if it is slack bus, voltage magnitude and delta both are known, that is specified, unknown quantities are P and Q. For load bus, P and Q are specified, right, but voltage magnitude and delta, these are unknown quantities. And voltage control bus, that is PV bus, right, P and voltage magnitude, real power and voltage magnitude are specified, but Q and delta are not known, right. So, with this in our mind, slack bus, PQ bus and PV bus, now we will move to see that first the bus admittance matrix, right. So, we will go for bus admittance matrix. I will explain everything, but I will put a question to you. For load flow studies, we use Y matrix, but not Z matrix. That is admittance matrix we use, but we do not use your impedance matrix, right, Z. We do not do. We make admittance for the whole thing. Why we do not use Z bus for load flows? This is a simple question to you, and answer also will be simple. So, this should keep it in your mind, right. Now, what we will do for bus admittance matrix, we consider this your what you call this sample 4 bus power system. This is a 4 bus power system, right. This is one generator, this is one generator, right. And for purpose of classroom exercise, what we have done is that R we have not considered, but when we will consider your what we call numericals, at that time we will take R, but here we do not want to complicate the things. So, only reactance is your what you call considered, right. So, this is your suppose generator 1 2 whatever is given, and this is your J.8, everything you assume it is per unit. So, this is J1, this for line 1 to J.5, J.4, J.4 and line 3 to 4 J. I think it is your this thing J.04, right. So, this is the sample power system, 4 bus power system we have taken, and this is the impedance diagram, but we have not considered your what you call that resistance, right. So, generally as you know from your this thing, that line admittance actually for line I to k, bus I to k, small y k, as you writing small y I k is equal to 1 upon z I k, right, small z I k is equal to 1 upon r I, z I k is equal to r I k plus j x I k. This is equation 1, right. This is the admittance, right. Now, what we will do, right, why we have taken this everything, these two sources, right, these two one you transform into your what you call that current source, right. So, instead of these two generators are given, right. So, instead of voltage one you transform into a current source, right. So, if you do so, look at this is the diagram, this is the diagram. If you look so, the figure 2, look this it shows that your what you call the admittance diagram. In that case, what you have to do is that you take a reference node. This node number is given as a 0, and this basically it is a ground and its potential is at 0 potential, right. That means, and these two sources have been converted to current source. So, this is your current I1 injecting this current I1 getting injected here, and current I2 from this side getting injected here, and all this your reactance thing has been converted to admittance. That means, it was, and as it is a current source, so this will be it is in parallel. So, that means, it is J.8. So, 1 upon J.8 is equal to your y, it is making as 1 0 minus j 1.25. This is 0 node, this is 1 node, that is why writing 1 0 minus j 1.25, right. And this is J1. So, 1 upon J1, that is minus J1. So, y 2 0, that is 2 to 0, y 2 0 minus J1, right, and this is your I2, this current is getting injected, right. And this line 1 to 2 voltage here 1 2 3 4, voltage are marked as V1, V2, V3, V4, these are the complex voltages, right. And this is 1 to 2, the reactance is J.5, right, or impedance you can take, R is neglected, that is 1 upon J.5, that is minus J2. So, admittance Y12 is equal to minus J2 is equal to Y21, they are same, right. Similarly, 1 to 3 is J.4, so admittance is 1 upon J.4, so minus J.25. So, this is minus J 2.5, right. And similarly, here it is also 0.4 J.4, it is also minus J 2.5, and here it is J 0.04. So, 1 upon J 0.04, that is minus J 25, right. So, this diagram, this one actually transform these two sources, transform into current source, and all the impedance diagram has been transformed into admittance diagram, right. So, that means, this is and one reference node is required, and this is your what you call, this is your ground, your normally it is a ground, and you can take it as a 0 potential, right. And this is the admittance diagram of figure 1, that is this is figure 2. I hope this is very easy to understand, actually not much is there, right. Next is you have to apply KCL to the independent nodes 1, 2, 3, 4, right. So, look, this current is getting injected here I1. If you apply KCL, right, at this bus bar I1, so what will be your equation? right, I1 should be is equal to, if this voltage is V, say 0 potential. So, if I make V0 is equal to 0 and this current is getting injected and you take all this current out, then I1 is equal to your first before my writing, I1 is equal to this take out. So, Y10 V1 plus Y12 into V1 minus V2 plus Y13 into V1 minus V3, but everywhere or your Yij or Yik is equal to Yki, I mean it both are same. Y13 is equal to Y31, small y, of course small y this one, small y12 is equal to small y21 and small y23 is equal to small y32, small y34 is equal to small y43. That means, this current at this one I1 is equal to Y10 V1, right, this thing, then you take this one and plus Y12 V1 minus V2, Y12 V1 minus V2 plus Y13 V1 minus V3, Y13 V1 minus V3, right, no equation number. Similarly, for this one I2 is equal to your Y20 V2 minus, I told you this 0 potential. So, basically Y20 V2 minus 0, basically Y20 V2. So, it is Y20 V2 plus your Y this current, that Y12 Y21 same. So, I will write Y12 only, Y12 into V2 minus V1, because current leaving from this 2 to 1. So, V2 minus V1. So, Y12 V2 minus V1, because Y12 to 1 same. So, not writing to 1, understandable, right. So, V2 minus V1 plus 2 to 3. So, Y23 V2 minus V3. So, here it is Y23 V2 minus V3. This is the second equation for the second bus bar, right. Now, third bus bar, here there is no current injection, this bus bar and this bus bar, because in this diagram it is nothing was given. So, no current injection, that means 0, right. That means this that means 0 is equal to, for the bus 3 you take all the outgoing current, right. For example, your Y23 into V3 minus V2, V3 minus V2, Y23 V3 minus V2, then Y13 V3 minus V1, because Y13 is equal to Y31. So, V3 minus V1. So, it is taken Y13 V3 minus V1, then you take this outgoing one, that is Y34 V3 minus V4 plus Y34 V3 minus V4, and no current injection here. So, it is 0 is equal to this one. This is the third equation. Now, fourth one, when you come here, right, this bus bar 4, right, current injection is 0, right, and this is, and if you take that 4 to 3, so it is Y34 V4 minus V3. So, 0 is equal to Y34 V4 minus V3. So, for the all bus 4, 1, 2, 3, 4, you have got these 4 equations, sets of equation. For the time being, not putting any equation number. So, this one from this diagram, you have got, we have got this one, this you have understood very easy, right, and from this you write down all these equations in terms of admittance, right, line admittance. Charging capacitance will come later, first you understand this. Now, rearrange this all these 4 equations, above equation, that means you collect all the terms to V1, V2 and V3. So, I1 you can write Y10 plus Y12 plus Y13 into V1, I mean this equation we are rewriting, then minus Y12 V2 minus Y13 V3. Similarly, this one also you can write I2 is equal to minus Y12 V1 plus Y20 plus Y12 plus Y23 V2 minus Y23 V3, right. Then this one you can write the third one, that 0 is equal to minus Y13 V1 minus Y23 V2 plus Y13 plus Y23 plus Y34 V3 minus Y34 V4, right. And last one, 0 is equal to this one minus Y34 V3 plus Y34 V4, that means we are arranging V1, V2, V3, V4 this way, right. So, this is your I1, I2, this is 2 current injection 0. So, we are rearranging, but no equation number is given, right. Once it is done, then you define, for example that you define capital Y11, capital Y11 is equal to y10 plus y12 plus y13. So, write capital Y11 is equal to y10 plus y12 plus y13, this was capital Y1, right. Similarly, first diagonal elements you define, then y22, this one capital Y22 you write y20 plus y12 plus y23. So, capital Y22 is equal to y20 plus y12 plus y23, these are only diagonal elements we are writing, right. Then third one, this y33, this is y13 plus y23 plus y34, the third one, that is your y33 is equal to y13 plus y23 plus y34, right. And this y44 is equal to the last one, y44 is equal to y34. So, capital Y44 is equal to Y34, these are all diagonal elements, right. Next you make off diagonal elements. Off diagonal elements, this one whatever we have from this for this equation, that y12, right, this is y12, capital Y12 you define, and y12 is equal to 2 1, you write capital Y12 is equal to capital Y21 is equal to minus y12. Similarly, this is V3, so it is y13, right. So, capital Y13 is equal to capital Y31 is equal to minus small y13. So, capital Y13 is equal to capital Y31 is equal to minus small y13, right. Similarly, you come to the next is your 2, right. So, y23. So, your what you call this is a symmetric matrix. So, your what you call y12 y21 will minus y12, here also 2 to 1 capital Y21 will be minus y12 symmetric. So, that is why it is what you call this y21 is minus y12 also, right, it is symmetric matrix. So, then 2 to 2 3 capital Y23 will be is equal to capital Y32 is equal to minus small y23. So, capital Y23 is equal to Y32 is equal to minus small y23, right. And then y34, right, you come to this one, these are symmetric matrix. So, directly you will come y34 capital Y34 is equal to capital Y43 is equal to minus small y34. So, capital Y34 is equal to capital Y43 is equal to minus small y34. So, these are our off diagonal elements, right. Now, when you write this equation, you write like this, I1 is equal to capital Y1 V11 plus capital Y12 V2 plus capital Y13 V3 plus capital Y14 V4. This way you write, some of them y will become 0, but make it like this, right. I2 is equal to, similarly again and again not again and again I am not uttering that capital, understandable. So, y21 V1 plus y22 V2 plus y23 V3 plus y24 V4, right. Similarly, I3 actually 0, I4 actually 0, some of the y's elements are also 0, but we make it like this first. So, I3 is equal to y31 V1 plus y32 V2 plus y33 V3 plus y34 V4, right. Similarly, I4 is equal to y41 V1 plus y42 V2 plus y43 V3 plus y44 V4. This way first you make, right, but now you see the connectivity of the line, right. So, but I3 and I4 they are 0, but we have to put them in matrix form. So, that means that your just 1 minute, that means in that your in figure 2 there is no, now there is no connection between bus 1 and bus 4. So, there is no connection between 1 and 4. So, actually y4 is equal to y41 is 0. Similarly, there is no connection between 2 and 4, right, that is why 2I24 actually y42 will be 0, and at this node I3 and I4 actually 0. So, also note that in this case I3 0, I2 I4 0. So, in this equation I3 I4 will be 0 and other two elements of y I told you that also will be 0, right. So, but for the sake of your mathematics and completeness, we have to make this equation I1, I2, I3, I4 is equal to, this is y matrix V1, V2, V3, V4, right. And this is actually, just hold on, just 1 minute. This yik equation actually 1 upon zik, this is actually equation 1, right. And this equation your I1, I2, I is equal to basically yv, this equation actually equation 2, or in general you can write that I bus, this is the bus current injection, I bus is equal to y bus, this is that bus admittance matrix y bus into V bus, this is the bus voltage, right. So, this is actually equation 3, right. So, we represent this equation basically in general I is equal to y V, right. So, V bus, now we are giving the nomenclature, V bus is equal to vector of bus voltage V 1, V 2, V 3 and up to V 4, right, and I bus is equal to your vector of the injected currents, right, that is I 1, I 2, I 3, I 4, but later we will see when you will form the Jacobian that when you choose one bus is slack bus, that voltage is known, right. In that case, we will see Jacobian matrix and other things will be how one can form, but this is the preliminary thing. So, y bus is that your I bus is the vector of injected currents, right. So, the current is positive when flowing into the bus and is negative when flowing out of the bus, this is the convention will follow, and y bus is equal to that bus admittance matrix, right. So, diagonal elements of y matrix actually is known as self admittance or driving point admittance, right. The diagonal elements, that is that y 1 1, y 1 2, y 3 3 and y 4 4, these elements diagonal known as self admittance or driving point admittance, right. That is in general capital Y I I is equal to k is equal to 0 to n, you write y I k, but k not is equal to I, right. That means, in that case also if you take your what you call that your including the reference bus, that is 0 to 4, if you expand y 1 1 y 2, you will get the same thing, right. So, and off diagonal elements of y matrix is known as transfer admittance or mutual admittance, that is y capital Y I k is equal to capital Y k I is equal to minus small y I k, right. This minus signs for small one, because this is each your branch admittance, right, 1 upon z I k. So, that is capital Y I k is equal to capital Y k I is equal to minus small y I k, this is actually equation 5, and this y 1 this y I I actually k is equal to 0 to n is taken and it is y I k, but k not is equal to I, such that, and later much detail I will explain when we will take this, right. And when we will if you that row wise y matrix later when we will consider charging admittance, when we will add the elements of a particular row of y matrix, at that time we will is something else, right. So, from that you can check out whether your y matrix construction is correct or not, right. So, this is that general thing. Thank you, again we are coming.